volume. It's like the Martian here, or Apollo 13.
Everyone say that.
Where's the speaker on this? I can maximize this by.
Let's see. Put your laptop normally.
Oh dear.
Okay, can everyone on the call see the
Yes,
shared screen?
yeah, we can. Yeah.
Okay. Right.
Go on, Richard, you introduce Tom.
So, everyone, we're going to hear from Tom, who is visiting us as well as to work on our ABCs. We've got a nice protein system, protein interacting with polysaccharides, that old chestnut. So, Tom, off you go.
Perfect. All right. Thank you, everyone, for inviting me to your group meeting. So, I mean, that title is actually left over from a conference, so probably ignore that, it's probably a bit wordy. But really what I want to talk about is pretty much why we're here today with Richard and Steve and what we're hoping to achieve. So, really the impetus for this work is looking at scarring and fibrosis. So, I'm sure everyone on the call understands what scarring is, at least on a basic level, because I'm sure most of you have personal experience of it. So in the skin is probably where we've seen it most commonly. You get an injury and the body evolutionarily has designed itself to close that wound as quick as possible. In closing it as quick as possible, it doesn't necessarily do a great job, and the skin that you are left with is not the same as the skin that you started with. And in conditions such as hypertrophic scarring, keloid scarring, you essentially get excess scar tissue, which can then lead to psychological and social difficulties. Equally, things following burns. So that was burns, that's my accent. And other larger traumatic events can lead to quite significant scarring, and especially when it's around the face, that can lead to quite severe disfigurement. It can also cause much more damaging disability. So obviously scarring in the eye is a great example of where you get blindness. Scarring in the internal organs like the liver and the kidney can cause serious disability and ultimately death. And another thing we're quite interested in actually is conditions like certain subtypes of a condition called epidermolysis bullosa, where through very small amounts of contact, this subgroup essentially develops blistering. This happens both on the external skin and also the internal mucosa. And they then develop a lot of progressive scarring eventually. So you can see in this image, there's essentially a fibrous capsule that's formed around the toes. That also happens on the hands. In the mouth, it just causes the mouth to close and close progressively, which you can imagine causes a whole host of difficulties. Scarring is complicated. Healing is complicated, and scarring is essentially the other side of the coin to healing. So, and I'm not a biologist, so I'm going to simplify this a lot, mostly for my own sake. So essentially there is an inflammatory phase where your body detects that there is a hole in you, essentially, sends a whole load of inflammatory cells to the site. That then encourages proliferation, it's been a long ass day, of those skin cells, which then need to start regenerating new matrix and trying to close that gap. And they do that basically through two mechanisms. One is by laying down new material, and the other is by closing it up. And that's where these myofibroblast cells come in. So again, by a complicated mechanism, but one of the key players through it is this protein called TGF-beta1, which is what we're here to do with Richard and Steve, causes normal fibroblast cells, which are the normal cells in your skin, to turn into these myofibroblast cells. And what these myofibroblast cells do, one is they churn out a lot more collagen, and two, they physically can contract the wound. And those alpha smooth muscle actin filaments that you see through that cell are what give it that contractile ability. So all you really need to remember from this is that alpha SMA and collagen are markers of upregulated scarring, if you like, which is what you'll see going forward. This is the slide that I absolutely don't need to cover for you guys. I'm sure you all know what polysaccharides are. The thing I really want to highlight about this, though, is that certainly compared to proteins, they are much less costly We know that they are generally quite stable in aqueous solution, at least if you put preservatives in them. You don't need to keep these at -80 or -200 like you do with a lot of therapeutic proteins. And we generally know what their toxicity is, know that it's low because we've been eating them for, what, 70 years, possibly more, putting them in processed foods. Now, in biomaterials groups like mine and Jen's, we commonly use these types of materials purely for their structural and release modulating characteristics. So we make hydrogels out of them, we make drug delivery vehicles out of them, we make tissue mimics out of them. But generally, we think of them as being relatively biologically inert. They're biocompatible, as we say, but we don't really think about them too much for their biological role, if you like. And there's a couple of studies that really kind of inspired this work, but this is the one I want to talk about. So this was a model of scarring in the eye, and this is a rat model. And the aim of the project was essentially to deliver very, very expensive protein therapeutic called Decarin, which I think costs between 100,000 and £1 million a gram. Obviously, to try and maximize the efficacy of that, is made into a polysaccharide matrix, essentially to extend the lifetime on the eye. So a typical eye drop will sit in your eye for about 30 seconds before you clear it, whereas I think this, we've recorded it up to about 8 hours. So for a protein drug that is that expensive, extending the lifetime of it, extending the activity time, really massively increases that benefit for minimal additional cost. But what we found is that actually, especially on the bar palette on the right, the vehicle-only control, so just the polysaccharide delivery vehicle with no expensive drug in it, was actually pretty effective. Not as effective as the vehicle plus the drug, but considering the fraction of a cost that it would be, actually not bad. So really, that's what got us thinking. Can we use polysaccharides to impart both the biological effect and also the material properties, which is the advantage of these materials, that you can utilize any biological properties they have, but also use them to create that structural and material properties that we might be interested in. So I would love to say that there was a rationale for the polysaccharides that we chose. Partly it was around what we had on the shelf at the time. Partly it was, there's a bit of talk about sulfated polysaccharides, especially for biomedical applications, which is why aortocarrageenan and dextran sulfate are in there. The others, Gelan, we just have a lot of that in the lab. We use Gelan for everything. Alginate, again, a pretty common one. And then methyl cellulose we put in because it's, unlike the others, neutral rather than being anionic. And to make a long story short, essentially what you can see is that aortocarrageenan in particular, again, if you can remember from that diagram I showed you, collagen bad, alpha SMA bad, and those SMADs are the internal transcription markers of those. It downregulated all of them really quite significantly. And then we also looked at the, so that's through PCR, which looks at genetic changes. Also looked at it in the actual cells, so what proteins are they churning out. And again, less dramatic, but a similar story where we saw that aortocarrageenan and to a lesser extent alginate really knocked down both alpha SMA and collagen, suggesting that it's having a biological effect, which was really exciting for us because this stuff costs absolute chips. We then looked a bit closer and we saw that this actually works in a concentration dependent manner, which is really useful to know. So the more polysaccharide that you put in, the more you downregulate both of these and the less scarring that you get, which suggests that there is a direct interaction between aortocarrageenan and TGF beta 1. There's a couple of other studies as well that kind of showed that suggests rather than it being a polysaccharide receptor interaction, it's a polysaccharide ligand interaction. Which brings us on to sort of the next part. So now that we have a polysaccharide that we think might have an bioactive mode of action, if you like, is then utilizing its structural and material properties to try and create a material out of it. And something that we're really interested in is spray delivery. So spraying has really high user compliance. People like spraying things. Part of that is because there's no direct contact between a solid and your body. It's really good for reaching hard to reach locations. So up the nose being a classic example, it's quite hard to get things up the nose via the roots. And it's very good at applying an even layer onto uneven surfaces without contact. So if you think about things like wounds, and going back to that epidermolysis bullosa example that I mentioned to you, if you're smearing liquid onto that, that would be quite painful. Whereas using a spray application, you can get a pretty good distribution onto that area without having to use immediate contact. So we attempted this, and the problem is that iota-carrageenan actually sprays really quite poorly if you increase its concentration that we would need to increase it to give it those useful material properties for targeting and retention. So essentially getting into the semi-dilute, if not concentrated, regime. And the problem is that this structuring prevents breakup and leads to poor spraying. So quite intuitively, I think you can kind of think about this as if you've got a completely entangled polymer solution. When you then try to disentangle it in a very short space of time over which the spraying process happens, it doesn't have enough time to disentangle and it doesn't break up. So you end up with quite a string, if you like, you don't get that breakup. So what we've been looking at is different formulation strategies to try and improve this. So one of them that we looked into was simply creating a phase separated blend. So essentially by mixing iota-carrageenan in this case with gel and gum, we were able to increase that spray area several fold, essentially by creating a microscopic checkerboard arrangement. So the carrageenan plays with the carrageenan, the gellan plays with the gellan, but they don't play with each other, they don't overlap with each other. And that essentially creates microscopic breaking points through which breakup can occur during spraying. The other strategy we employed was, I've called it ionic discretization because it sounds clever, but essentially shucking a load of calcium into it. Actually, it has to be in quite a specific way. So for carrageenan, I'm sure a lot of you are aware, you need to heat cycle it from a powder to make it expand and then overlap with itself to give you a viscous or viscoelastic material. You have to put the calcium in, and it has to be calcium, it doesn't work with sodium. It has to be calcium, it has to go in after it's already cooled down. If you put it in hot, it doesn't work, and that's because you need that calcium to sit in between the different fibrils rather than inside the fibrils, which is what you get if you put it in hot and then cool it. I do have data to that effect, but I apparently haven't put it in this presentation, so I apologise. But you kind of see that here. So if you just have a concentrated carrageenan solution, you get no microstructure because it's all just overlapping on a smaller scale. Whereas if you include, frankly, quite high concentrations of calcium chloride in this specific way, you can essentially create this discretization. And as I mentioned, you can kind of imagine that this gives you those microscopic breaking points so that when you try and spray it, you get breakup through the low polymer density regions, but you maintain a lot of the material properties through the presence of those high polymer density regions. The other things you can do when you have concentrated polymer solutions and gels and that kind of thing is start looking at other functional properties. So one that we were interested in, again, because of these epidermolysis bullosa patients who are interested in using this in their mouths to prevent progressive scarring, we were interested in mucoadhesion. So how specifically can we get these materials to bind to the mucosa? And another one that we looked at was lubrication. So both in that patient cohort and others, dry eye is an issue, but also in the mouth for this population, it's sort of actions like chewing and brushing the teeth that cause the friction with the internal mucosa that then sort of leads to this cascade of scarring happening. So actually by imparting lubrication, which we showed that we can, you can almost prevent this from that length scale. I didn't include the data again for time reasons, but we also showed that you can anionic polysaccharides certainly interrupt collagen fibril formation. So actually what we showed is that by using carrageenan and incorporating it into this structured fluid, you can essentially prevent scarring on 3 different length scales, which I thought was quite cool. Thing is, and this is ultimately the reason why we're here to work with Rich and Steve, why these polysaccharides? So I mentioned at the start, we picked, in essence, a few random ones off the shelf, and iota carrageenan happened to show decent activity, which was really exciting. We don't understand is why. So we tried dextran sulfate, and that showed no activity in the cell model. So it can't just be the presence of sulfate-dependent groups. Here we looked at a couple of different polysaccharides, so different variants, sorry. So we looked at the kappa, iota, and lambda variants. For the alpha SMA readout, which is, I guess, the main one we're interested in, iota does seem to be the most effective. On the collagen readout, that's not true, and actually lambda's the most effective. So there's clearly more work we need to do here to try and suss that out. Equally, in the those other 3 bars, LV, MV, and bio, are essentially different types of alginate, which I mentioned does have some, but not as much biological activity. And actually, again, not through the collagen readout, but certainly through the alpha SMA readout, it appears that increasing molecular weight increases its activity. So on a weight-to-weight basis. So this is essentially what we're trying to tease out now. We've found an effect. What we really want to try and hone in on is what are the properties of these polysaccharides that actually lead to this effect arising? Why does some work better than others? And there's a lot of factors that could be at play. Obviously, dependent groups, the chemistry of the backbone, the flexibility of the backbone, the molecular weight of the polymer. And hopefully that gives a lot of understanding, not only about how this interaction works, not only about which polysaccharides might be most effective in these applications, but I mean, a potential slightly more blue sky goal is creating completely new chemistries that maximize the properties that we found from these natural polysaccharides and actually making synthetics that dial up to 11. So mechanism really is what we're hoping to find. So we've got some preliminary DLS that suggests that, as I mentioned, it does form an aggregate between the polysaccharide and the protein. That's what we're hoping to see and delve into a bit deeper through the analytical ultracentrifugation work that we're doing now here in Sutton Bonington. We've got a little bit of data from a technique called FIDA, which is flow-induced distribution analysis, which, if you're a chemical engineer like me, is a really interesting technique because you essentially shoot your sample down a pipe. It then forms a parabola, but the diffusion sort of out of that parabola, both backwards and forwards, then obviously depends on the molecular weight of the diffusion. So essentially, we use this technique to show that by going from the pure protein to the protein in essentially a field of the polysaccharide, that you get an increase in hydrodynamic radius, an increase in spike count, which essentially is aggregates. And also, I am assured that this final chart means something, but I can't for the life of me remember what it was. So really, that's what we're trying to do, is sort of piece together through a host of different techniques to try and understand this interaction, both more closely the interaction that we have, and also and how specific this is. And this could also have applications beyond scarring. So again, we're looking at one protein that's involved in scarring. There are lots of proteins that are involved in scarring. Many of these have what are called heparan binding sites. So it's interesting whether this is only applicable to proteins with heparan binding sites. Is it applicable to all proteins with heparan binding sites? We don't yet know. Could this be interesting in wider areas? So platelet aggregation, we know that some carrageenans have, again, similar to heparin, platelet aggregation for hemostasis. Could this be useful in, again, antivirals? We know that carrageenan is antiviral. So could it be useful for some of those applications? So that's all from me. Thank you so much for listening. Just to wrap up, some polysaccharides are antifibrotic, others don't seem to be. The mechanism is likely, and since I wrote this talk, I think increasingly like what we see to be complexation between TGF-beta and polysaccharide. And hopefully we can then translate these into essentially one component biomaterials, or maybe two components, but hopefully without too much complexity. So with that, thank you very much for your time. I'd like to thank all my collaborators, all of Birmingham, Nottingham, Richard and Steve, and Phil, who did that FIDA stuff with me at Aston. I don't think there are any postdocs on the call, but I encourage you to apply for Rose Trees funding because they did a little bit of funding for this. And it's one of the few funding pots that postdocs can actually get. It's not very much. Yeah, you can't get any time on it. You get it. I think I got £8.5 grand.
Right.
So it's basically signing yourself up for double work, but it is a pot of money that you can put your name next to, which is obviously nice for job applications and stuff.
Sounds great. Well, thanks, Tom.
Yeah, cheers, man.
Presumably, this carrageenan or whatever polysaccharide you use or combination use can be applied to, say, pulmonary fibrosis in the lungs, which is scarring of lung tissue as well. So it's got a wide range of potential application here.
It does, yeah. So TGF-beta is pretty central to almost all types of scarring and fibrosis. There are advantages to looking at external applications like wounds inside of the mouth and that kind of thing. One, in that they're easier to target, and two is that they're naturally or unnaturally cleared. One of the issues I think we have with things like polysaccharides is they're not broken down in the body. So if you fill the lungs with carrageenan, there's not necessarily a natural way of it getting back out again, which actually might cause more problems, or not more problems, but similar problems to.
Well, there's the transport pathway of the mucus getting out. So as long as it's bound to mucus, it can then.
The mucus will clear it. I think.
Potentially, yeah.
Glad, Jacob, would the mucus in the lungs clear any remaining carrageenan, or would it lead to pneumonia?
I mean, it's so it's hard. First of all, it's interesting in terms of how the carrageenan. So first of all, Tom has a great presentation and great work. So first of all, it's super interesting because it seems to be the carrageenan. So I have kind of, obviously you put out a disclaimer that you don't understand the mechanism, and it's still very much your research avenue to understand what specific chemistries and physical chemistries are involved in this process. So if you think about iota-carrageenan, so you did the concentration dependence, which is very good, because it means that yes, it is to do with some binding, because obviously if we change the concentration, then the binding reaction is changing in terms of so it would be interesting to see what if I kind of may suggest is to see if we can look at the iota-carrageenan with different molecular weight and see if there is an effect of molecular weight. So with the same concentration but different molecular weight, is it just you need the relatively short chemistry, short length chemistry, and it's sufficient, or you really need to sort of, this is also comes back to your film forming capacity, because then you kind of say, right, I don't care about the film forming capacity of iota-carrageenan, I'll just choose the polysaccharide with the best film forming film forming properties, but I embed let's say low molecular weight iota-carrageenan as an active ingredient, right, as an active polysaccharide. But then you just don't struggle if iota-carrageenan on its own doesn't form nice. So my question is, so that was a suggestion. My question was really about the mucus interaction. So because Jacob was having his head up, he was doing a lot of work looking at the mucin blends with and mixtures with different polysaccharides, and we're finding very interesting effects in different concentrated system. So it definitely would be interesting to look at, and especially look at the effect of calcium, how that impacts this interaction. And I think this is where,
Yeah, I think something that's worth saying actually is for the mucoadhesion, what we found is actually the Gelan that mainly made it mucoadhesive, not the carrageenan.
yeah, which is not surprising because Jalan is also has negative charges in that case. So and it's been we've seen the adhesion of Jalan to a lot of different things. So it has this particular stickiness, which is definitely something that Jalan is quite known for. Yeah.
Yeah, if you want
Jacob.
mucoadhesives, Tom, then chitosan or aminocellulose, which is
I mean,
has
I would.
Charge though.
chitosan, which you can
Yeah.
control the properties.
I mean, Gleb's absolutely right in kind of thinking about molecular weight. It's one avenue, but iota carrageenan, does gel form in the presence of calcium, but there's like kappa 1 and kappa 2 carrageenan. So these are gel forming in the absence of calcium. And I think there's a third one, lambda carrageenan.
Yeah,
it doesn't form a gel, but it has
Lambda
like
doesn't gel at all.
Lambda's
really
gel
Yeah.
at all.
No.
So iota, I did make a point of saying it had to be a boatload of calcium because it gels in the presence of calcium, but it also forms weak gels. And that's the problem when you're trying to microstructure them, because you can form it into a microstructure. I think I showed you it very nicely. The problem is if you leave it over time, the polymers will then wiggle out of that microstructure and start re-overlapping. So while iota appears to be the best biologically, actually what Jen is focusing on is kappa carrageenan, which, as you say, gels in the presence of sodium, but also forms strong gels. So while the biological effect might not be as good, it's still very much there, but also the making a sprayable material out of it actually should be hopefully easier.
Yeah, I mean, so I'm working on it as a 3D printing, in 3D printing for vascular networks.
Yeah.
So it's a really, it has these kind of strong gel forming, but it's really good at maintaining mechanical strength over time. It doesn't kind of phase separate, it doesn't deplete. So maybe embedding it within these things, and it's something to really look into, kappa. And then, as Gleb said, kind of start to deconvolute the physical properties of the actual polymer itself.
Yes.
And then think about if there's any kind of cutting you could do, like enzymatic kind of snipping, lowering the molecular weight, things like that. It'd be really, really, really cool, I think.
Yeah, no, I agree. And that's something Jen's trying to do, isn't it? Is put carrageenan up and see what it does.
There's quite a few different ways to depolymerize, so I think.
Yeah. I say we started with Algenex, we could buy it. It was
Yeah.
Well, Jennifer was doing that, Jennifer,
Yeah.
with the chitosans for the Osberg project.
Yeah. Well, so was
Using the
in fact, while you're here, I think it'd be really good to dig out Fahad's PhD because he did depolymerization of carrageenans to then get some information about its conformation. So if we can try and find that, I assume we have it in the office somewhere.
We will have a look.
Okay, cool. But I was thinking about, the spray pattern, and you were saying that at a certain concentration, it then just became like a splat, right?
Yeah.
Well, for me, that kind of sounded a bit like C star, where it just hits this critical overlap concentration, which you can get rid of by reducing the molecular weight, or at least reduce the impact of it.
Yeah. By reducing the molecular weight, you reduce the viscosity.
Yeah.
Or intrinsic viscosity.
Yeah. So I guess then a case of if you get the same weight to weight biological effect from shorter chain, then
and this is the trade-off you're going to have. But
the problem is, even if you do that, if you go below, the advantage of having it above C star is that you then get all the material properties that you want because it's entangled. You get massively enhanced viscosity. You get potentially viscoelasticity, which you wouldn't get if you went below C star.
Yeah.
So that's what we're trying to do. That's why we're playing around with the microstructure. Is we're trying to get best of both worlds.
Yeah.
And you want that. You want
that.
Yeah.
So it just by the physical properties, it will stay where you want it the longer. You can potentially target it better. Again, I didn't put it in this presentation because it has to carrageenan, but we showed with a alginate acetic acid system which was quite neat. That was for burn wound infection prevention, because acetic acid is quite a good antimicrobial, by increasing the acetic acid concentration, so increasing the overlap. We got better spraying and also massively increased viscosity and viscoelasticity of huge orders of magnitude, which is really exciting. So we can actually get both at the same time, which is previously pretty unheard of, because it was previously viscosity goes up, sprayability goes down, and that's that essentially.
So yeah, I mean, is there a mechanism that you could start to think about elucidating in carrageenan and things like helix aggregation? I mean, is it forming, trapping things within a helical nature, or I don't know, just a shot in the dark?
Potentially. Yeah, no, absolutely, potentially. So that's something else that Jen's going to be looking at. I tried to look at it once and it didn't go well, and I had better things to do. Other things to do, so I stopped doing it. But yeah, especially with the kappa, looking at the difference between how it works as a free polysaccharide versus how it works as a fluid gel versus how it works as a quiescent gel. And yeah, pretty much what you were saying is, actually, does the conformation over and above what it does as a single molecule, can it trap things? Or the opposite, does trapping the polysaccharide in a gel conformation stop it from interacting with the protein potentially?
Yeah.
Again, the answer is we don't know, and hopefully Jen's will find out. No pressure. This is really fun. I love just saying that Jen's going to do stuff. It's great. Please.
But this has got all sorts of possibilities here.
Yeah.
Like, if you're going to use it for dealing with fibrosis in the eye and things, then you could almost use it as a one-stop shop, because they currently use polysaccharides in the treatment of dry eyes and things.
Yeah.
And the candidate ones used are generally carboxymethylcellulose, hyaluronic acid, tamarind seed gum, and combinations thereof. But if carrageenans do the same thing, and you get the added bonus of dealing with fibrosis, then come on.
Win-win. Yeah. Exactly.
So what are you proposing to do in the AUC work? Are you kind of just looking for binding between the protein and the mucus? Or is it
currently we're looking at just the binding between the carrageenan and the TGF-beta.
Yeah.
And I'm pretty sure we've achieved that, haven't we?
I was doing a bit of a dance earlier, so I think we're fine.
I was going to say,
It forms bricks,
using
basically.
that fancy new software that he's developed. That's
I
brilliant.
was going to say, me and Jen don't understand the.
It was not with the fancy new software.
Some of the technicalities, but we understood the dancing.
Yeah.
So we took that as a good sign.
Because gelation occurs over really, I think it's really wide ionic strength ranges. So, are you going to do anything with the ionic strength in the medium you're analysing in AUC?
Essentially, yeah. So there's three things I think that we particularly want to look at. One is specificity. So now that we've hopefully got the concentrations and parameters for TGF-beta and carrageenan, or kappa carrageenan in this case that we've used, start changing them around. So if instead of TGF-beta it's BSA, or it's TNF-alpha, or it's essentially other proteins, is that specificity still there? Does it still form that, not aggregates, we're trying to avoid aggregates, aren't we? But does it still form that complex?
Yeah.
Or does it not? Equally changing polysaccharides, so looking at the different subtypes of carrageenan that you mentioned, Jacob, so kappa, iota, lambda, looking at other ones, looking at alginate, and then potentially down the road looking at scissions of those molecules. It's really trying to understand, if we start changing around proteins and polysaccharide combinations, do we still get that specificity, and then using that information to go back and say, well, how did that molecule differ from that molecule? Actually trying to then backtrack and work out, well, what must be the interaction here. Second one, as mentioned, is looking at different solvents. So, I mean, we've now done this type of work 3 times with 3 different solvents. So the DLS that I've got is in cell media. We've done it in sodium chloride. Today we're doing it in PBS. So again, trying to understand the range, and I guess that's more of for us from a translational point of view, is what is the environmental range over which this will work. Does it not work in acidic conditions? Does it work in high osmolarity conditions? Does it only work in low osmolarity conditions? That kind of thing, in addition to understanding the interaction by changing those things around, which I probably understand much less than Richard and Steve. It's a good job that they're here. But as I understand, that's the kind of thing we can start looking at. And to again, looking more specifically by, I think the plan for tomorrow is to start changing the carrageenan concentration to try and look at binding curves, essentially, to try and understand that interaction more closely. So those kind of three avenues that we've been busy so far.
As a kind of bolt-on study, just in the translational aspect, it might just be worth doing microbial, because has antimicrobial properties, also seeing if these things that you're starting to generate, or the things that you're targeting for the interaction, or seeing where the mechanism is, just have see if it kind of prevents bugs from growing as well, because that you really want that to maintain the effect. If you're spraying something in the mouth or spraying something on the eye, you want to kind of keep it clean as well. So if it has an underlying dual effect as well, that'd be really, really cool, because I know that it's carrageenan is kind of antiviral, antibacterial, and has anti-cancer properties as well. So
well, all of them, Jacob.
No, carrageenan generally, but I'm not sure which specifically. I know that lambda binds to viral particles. So
we developed a nasal spray for antiviral that's got iota in it. Confident about the antiviral. Antibacterial I've seen less, if any, of.
Yeah, because it'll have applications in microbial keratitis, things like that. Yeah. So as a spray and removal. So alternatives or adjuvants to antimicrobials.
Yes, I don't know if it has an antibacterial property. That's not something I've come across, but it may well do.
I wonder what the mode of action of that is. Would it bind with the EPS?
I think
quite possibly because I like to think of EPS as three little piggies, a house made of hay, sticks, and bricks. So it might just kind of really just make the EPS so viscous that they can't communicate, the bacteria start to die and things like that. So yeah, there's lots of cool things that at play with the kind of open organ environments,
Yeah. Something to look into.
Yeah.
That was Google,
Evidence of it.
Yeah. I mean,
happy to offer those work packages.
Thank you. Yeah, something that I'm particularly wary of, I don't know if you guys are similar, is that a lot of the polysaccharide healthcare research, as a research in slightly inverted commas, does seem to be polysaccharides from traditional medicine, and they just claim anti-everything properties.
Preach.
Which is why I'm really keen to get the mechanism of this and actually dig into them.
I actually refused to review a paper that was in the carbohydrate polymers, and I was saying look guys, I'm not going to review this because they extracted some polysaccharide from chaga fungus, and then they say
something.
Yes, extracted something. Okay, polysaccharide, fine. You can do Dynex and check that it is a polysaccharide. And then they say, oh, it is the anti-cancer activity and stuff like that. And so, no, come on, give me a break. I mean, you can't just put one cell line and say, oh, the cancer cells are dying, and then you don't have proper controls. You don't have anything, and it's just to. And I said, I'm not going to review this paper, and it's not even rejection. I just don't want to even consider that. So, and I understand you try to sound like the carbohydrate community is really cool and anti-cancer and things like that. And I think there is a merit in exploring these things, because we know some of the polysaccharides are extremely bioactive, like you are showing here. But the sort of the stretch to where they go and what is the strength of the effect and how it can be contextualized in the case of the disease, not just the cell model. That's, of course, is something that we need to be very much aware. But I think this is a very strong case. I think it would be really great to see if there is this complexation and how strong is the binding and what the mechanism of the binding.
Yeah.
So probably even just doing some circular dichroism. That would be really interesting to see, just so that we can pick up on any changes in the secondary structure associated with the binding. So
That's a great suggestion, Mickey.
yeah, it's kind of I think it would be really interesting, and because it is, you said, like, I mean, depending on it's not all factors are affected mostly by the carrageenan. Some of them are, it was at lambda, right? So the kappa, which one was the other one that has for the collagen? For the collagen
Oh yeah,
one.
I think that's something we'd want to repeat before
Yeah.
saying anything strong about that, because in theory it should be a single mechanism, so both should track at the same time. It's a bit suspicious that one goes down and the other doesn't, unless it's an extracellular effect. So it's not that it's stopping collagen from being produced, it is somehow stopping it
because
being
do you know
detected
if
after.
this because do you know if those polysaccharides you've tested are of roughly the same molecular weight?
I suspect that they're not. We don't actually know, and that's one of the things that I'll be very open about, is that actually in our research group we don't have access to a lot of the techniques that you would want to use to do. Yeah, which is why we're collaborating with.
So you can come to us for the molecular weight. You can come to us. Yeah.
Yes, I think
it's because we have
slowly penetrating the chemistry department at Birmingham.
We have the asymmetric flow fractionation with the moles detection. So I mean, we're working with Steve on that. So we are. I mean, the Dalal is a student who's looking at the binding between mucins and protein. So yeah.
We've had SecMals for 40 years, but sadly, with me being emeritus, that's one thing we haven't really been able to maintain is our SecMals facility.
Yeah.
We stopped at the DLS on the other side, but Gleb's got a great system now, and because we've got this combined laboratories now, including you, Jacob, in Cardiff.
Yeah, exactly. So Tom, just drop me a line, and if you see Richard, say hello from me.
Richard's here.
I'm right here.
No, Richard Moakes.
Oh, Richard. Awesome.
Sorry, Richard. Sorry, Richard. Yeah.
Yeah, it's great. I mean, I really I remember putting you guys in touch, and it was like, right, I think there's a really good bit of work here to kind of go over you, Richard. It was nice to kind of go to Birmingham and see your work and research. But yeah, I mean, I have to go now, but please send my best to Liam. And it seems like
we're just about to wrap up now anyway, Jacob.
Yeah.
It seems like really promising work.
It is very exciting.
Molecular level interaction and scaling that up is going to be really cool.
Anyone got a quick point before we say goodbye? Anything else?
If anything comes to mind, I'll drop a line.
Especially with
I'll via email. Yes. Okay.
We'll do you over for a talk at some point as well, which would be really good. Yeah. To Cardiff.
Absolutely. Jacob, did you get that grant funded?
I'll find out in June or July.
Yeah, because my son's just got funding. I think I said that
right.
Time, didn't I? Yeah, with the AHRC. So he's the same boat as you, really.
We just got a grant unfunded by EPSRC. So that was
EPSRC, they said it was 11% success rate.
So it was 4% success
4%. So it's impossible. It's impossible. No, 4%.
We'll go to Rose Trees and
no, but 4% is impossible because the subject of getting a grant is having a Nobel Prize, because unless you have that, there is no chance. So they say, who we fund, the Nobel Prize winner or we fund Gleb? And then, of course, they fund the Nobel Prize winner. I mean, without disrespect to yourself, and not like a low self-esteem thing, but it's the obvious thing. If the 4% success rate, then
Right, I'll
there
change
is-
my name to Sledberg then. That might be.
Yeah, exactly. All
Yeah.
right, everyone, it's great. Tom,
Yeah.
great to see you, and
Great work. Great to see this. Yeah.
great to see you, everyone. Thank
See you,
you.
everyone.
Yeah, cheers, guys.
Cheers.
Thank you.
Cheers.
Bye-bye.
And once again, thanks, Tom.
Yeah, thank you.
Thank you, Tom.
Good stuff.
Cheers, thanks, guys.
Right. Morning.
All right. Yeah. Great stuff, guys.
Oh, hang on. Jacob's still there.
Yeah. If you need anything Cardiff way, let me know. It'd be great to see it. As well as kind of, I don't know if you want to, because we're starting to do 3D bioprinting with Carrageenan. So if there's any applications in terms of that,
Yeah, because Birmingham's not that far away from Cardiff, but
yeah, let me know. So yeah, please do. All right. Great stuff.
Right.
Yeah, the good trend.
Especially if you're on the right side of Birmingham anyway, you're
Yeah.
on the,
Yeah.
That's fine.
University side. Right. Great
All right,
stuff, Tom.
Jacob.
Nice to see you, Steve. Nice to hear your voice,
cheers
Rich.
then.
See you, Jacob.
Take care, guys.
Bye.
So